Log on, tune in, find out. Another good idea from Cambridge.
Of this afternoon is Professor Yousuke Ohyama from Osaka University. He speaks on analytic solutions to the q-Painlevé equations around the origin.
Thank you very much. And thank you for organizers. So it's my great pleasure that I can come back here again, so 3 years ago. So I enjoyed Cambridge and enjoyed this workshop program. And so the audience also enjoyed everything. So please relax in the last session in the afternoon. Okay, so I'll talk on some analytic solution of some q-Painlevé or continuous Painlevé equations around the fixed singular point. So I'll talk on the three topics. One is classical Painlevé fixed equations. The second is QP6. The third is QP1. So at first, I'll give some start from the simple exercise. It's a simple exercise for a freshman course on linear algebra. So take 3 2x2 matrices, determinant equal 1, and multiply 3 equal 1, and give a trace. Then what is M0, M1, infinity? This is the simple exercise. So you can solve this problem very quickly. M0, M1 is like this. M1 is complicated, but like this. And M infinity can be determined by M0 and M1. Of course, you know these three matrices give essentially the equivalent to the monodromy data of Gauss-Euler's hypergeometric equations. And the important thing is the matrix elements are completely determined only by local exponents, from ABC. And I treated only some non-resonant case. So if A or B is have an integer, we have some logarithm sum or a Jordan block, but I omitted. But you can also solve it even in the resonant case. And we denote these matrices MJ is MJ ABC. ABC is a local exponents. This is very, very quite simple. So the monodromy data of Gauss hypergeometric equation can be solved by even in the freshman mathematics course. Okay, so this is not the exercise. This is a problem. How about we start from the 4 matrices? So that we start from 4 SL2 matrices and give trace. And multiply only one. Then what is M0, MT, M1, M infinity up to adjoint? This problem is very, very difficult. So I think so. Most of freshmen cannot solve this problem, but we can. We know this is space. So it is called monodromy spaces or characteristic variety, or classically it is called Frick cubics. This is found in you can find this cubic in Klein Frick's famous book on automatic functions. And so take some 4 SL2 matrices. Then the parameters number of the parameter is 6. And 6 is 4 plus 2. 4 is the number of the parameter C4. And there is some fibration to this monodromy space to the C4, MJ to trace MJ. And each fiber is 2-dimensional spaces. And this is essentially equivalent to initial value space of the Painlevé 6. This initial value space is analytic version of the initial value space. It is different from Okamoto or Sakai's initial value space. Okamoto's initial value space is algebraic. So it's a rational surfaces and has some infinite divisor or something. But this is cubic, it's the analytic part. And there is the correspondence of Okamoto initial value spaces and this Frick cubic. It is called Riemann-Hilbert correspondence. This is the algebraic part, this is the analytic part. And also, therefore, this Riemann-Hilbert correspondence is completely transcendental map. Painlevé transcendent. So it's some analogy of the famous elliptic curve. So elliptic curve has 2 forms. One is y-stress form. This is algebraic. But there's another analytic aspect of the elliptic curve. It is torus, just torus. Just torus is torus is analytic part. So, but the algebraic part of the elliptic curve and the analytic form of the curve, there is a correspondence by pair function. This is also transcendental map. But Painlevé function is more transcendental than elliptic function. So it's very interesting to consider some very special value of elliptic functions or modular functions. In the same way, it is very, very interesting to find a good special value of this Riemann-Hilbert correspondence. This is my problem. So I'll start the next problem. I add one more condition. Suppose M0 and M2 commute. What happens? What happens? This is just simple exercise of linear algebra. We can determine M0, M2, M1, M3 by the only local exponent, like this. There we have two solutions. So exchange some exponent like this. So since M0 and M2 are commute, so we can diagonalize in the same time, like this. And M1 is like this. It's the same as just the same as hypergeometric. So if M0 and M2 commute, the monodromy data is very similar to hypergeometric. Then the problem is why this is so simple. Because I think this is very connected to some rigidity. If so we have generic form matrices M infinity, M1, M0, then we have two-dimensional spaces, Greek cubic. But if you add one more condition, M0, M2 commute, then it becomes zero-dimensional. The monodromy data is almost hypergeometric, and also determined only by local exponents. This is I think it's related to rigidity. This monodromy data is not rigid. It has two parameters, two axis parameters, so not rigid. But this case is very close to rigid systems. I don't know the reason, but I remember I believe this. So I give some definition of the monodromy data. If we can determine MJ explicitly only by local exponents, we call this monodromy data is monodromy solvable. This is my definition, and this is not standard term. So, I believe this definition is very, very important to study linear differential equations. So the simple example is three matrices is monodromy solvable by Riemann, and if MI, MJ commute, four matrices is monodromy solvable. Then, so this is four matrices corresponding to Painlevé equations, Painlevé 6 equations. What Painlevé equation corresponds to this monodromy data? This is the second problem. So I'll go to the Painlevé equation, monodromy preserving deformations. Painlevé equation is given by the monodromy compatibility condition of these two equations, and this is give the monodromy preserving deformations. So I give the second definition. A Painlevé function y is called monodromy solvable if the first linear equation is monodromy solvable at the previous definition. So we'll find Painlevé functions with linear monodromy My, Mj equals 0. Of course, if you take any My, Mj from 4 to 2 from 4, then it becomes monodromy solvable. It is evident. So the answer is very simple. Painlevé 6 is like this one, and t equals 0, 1, infinity is a singularity of the Painlevé 6 equations. And it is kind of the Boolean-Book type singularity. Boolean-Book type singularity is some nonlinear analog of regular singularities in the linear case. So that's why if there is a formal solutions at Boolean-Book type singularities, the formal solution converges. And around t equals 4, we have 4 meromorphic solutions. This is the initial value. And alpha j is corresponding to the parameter alpha, beta, gamma, delta. So it's related to the local exponent of linear equations. So this is the theorem. So for any meromorphic solutions around the fixed singularities, the monodromy data My, Mj commute. And around t equals 0, M0, MT commute. These are the two matrices, monodromy data like this. And another two is M1, M infinity commute. And the other singularity, t1 equals 1, t equals infinity. then we get all of the monotomic data. The 2 of 4 commutes, M1, MJ equal. So there are 12 monotomic solvable Pauli 6 equations. And each Pauli equation functions, the 2 monotomic matrices commute. To prove this,
when you talk about meromorphic solutions, so just to make sure I'm understanding you, you're saying these are places where one of the essential singularities becomes meromorphic?
no, it's in general, Pauli transcendence has an essential singularity at a fixed point.
Yeah, and
Yes.
so these special cases are where one of those essential singularities.
Yes. That's
goes away and
yes.
it's just a pole.
Yes. So this is very, very special solution.
Okay.
But not transcendent, but this in general transcendental, not hypergeometric, not algebraic.
Yeah.
Of course, so you take some special parameters. So for example, alpha 4 equals 0, so something, this becomes a hypergeometric or something. But in general, generic parameter, these are not classical solutions in memory. To prove this, we use a technique of clustering singular points, as Marta explained. Frank is gone. Frank asked about clustering singularity, as Marta talks about. So clustering singular point is like this. So this is the potential of X. This is equal to like this. This is simple. Very, very simple. Like this. So if you take a limit t equals 0, then there are no essential singularities. T equals 0, this is 0, t equals 0. This is true for meromorphic Pauli equations. But for generic Pauli transcendence, so as Professor Ryan tells us, so the Pauli transcendence has an essential singularity around t equals 0 in general. So that's why this part, AT, also has essential singularities around t equals 0. That's why you cannot take a limit in general. Sometimes it may be non-zero, sometimes 0. So Davide knows very well. So Davide studied the local behavior for generic Pauli transcendence. So there are infinitely many zeros or infinitely many poles around t equals 0. That's why you cannot take it. But for meromorphic solutions, meromorphic convergence, in this case, TAT goes to 0. That's why we don't have no irregular singularities. Then this goes to the hypergeometric. That's why we can determine monotomic data for meromorphic Pauli 6 transcendence. This is a Pauli 6 case. To tell that this result is not my result, but my student, Dr. Kaneko's result. He's a very, very strange guy. He took, this is a Japanese newspaper in March 27, 2 years ago. He took the doctor degree. He's 71 years old. He took the mathematical degree of science and mathematics when he was 71. Also, this person is Kaneko. So not this is girls. This also some new doctor in Osaka University, but also he took the doctor degree when he's 70 years old. So I should study mathematics until 70 years old or 80 years old or 90 years old. So he's now he's still working on the Pauli equations or the nonlinear integral systems. So I should work more harder than Kaneko-san. So this is a newspaper. He is reported in many newspapers or televisions or radio or something. Okay, so this is also Kaneko-san's great work. So I'll start. So I was influenced by Kaneko-san's work. I start q-Painlevé equations. This q-Painlevé 6 found by Jimbo Sakai. If you remember Sakai's talk 3 years ago, at first he wrote Pauli 6 equation, continuous classical Pauli 6 equation without this note. But next, he tried to write down QP6 without note. He missed some parameter. But anyhow, it's okay. It's Sakai-san's work. So it's very simple, simpler than continuous Pauli 6 equation. How about this equation? So there are some many works. So this is more than 10 years ago, but after Jimbo Sakai's work, there are many works on q-Painlevé equations, but and Jimbo and Sakai found QP6 by connection preserving deformations. But we don't find any analytic result on QP6, some connection preserving deformation or something. So connection monotonically preserving deformation is very, very important to study in continuous Painlevé equations. So I believe connection preserving deformation is also important in q-Painlevé equations, but there are no such results in these more than 10 years. So it is a good problem to study q-Painlevé equations using the technique of connection preserving deformations. So that's why I was this way. So in the same as Kaneko-san, my students, so I follow my Kaneko-san. So find the meromorphic solutions around t equals 0. And then determine the connection matrices of the QP6. So this is Q analog of Kaneko-san's solution. And the meromorphic solution is easily to calculate like this one. There are two singular points at t equals 0 and t equals infinity for QP6. And each of there are four, I forget 1, 2, 3, 4. There are so 4 meromorphic solutions at t equals 0, 4 solutions t equals infinity like this one. 4 generic parameters. So we can determine connection matrices for QP6. What is the connection data? So this go back to the Jimbo Sakai's paper. Sorry. Because I mentioned, so there are no definition of Q-Boulier-Bouquet singularities, but as the same as the continuous Boulier-Bouquet theorem, so we also showed there are some unique formal series and it is convergent. It is completely the same as classic Boulier-Bouquet theorem. So that's why this formal series is convergent. Okay, so this is just a remark. So we go to the Jimbo Sakai's connection preserving deformations. Jimbo Sakai gives the QP6. At that time, so there are no Q analog of Painlevé 6 equations. And Jimbo Sakai has studied some of the compatibility condition of Q linear equations. So A is like this, so it's like a Q analog of the linear equations. And like B is some deformation parameter. Give the deformation connection. This is data. So please see the Jimbo Sakai's paper. But I should list up Jimbo Sakai's data. So when you download my PDF file from Newton Institute, this is the same as Jimbo Sakai. Then for meromorphic solutions at t equals 0 or t equals infinity of QP6, the linearized equation also reduced to the basic hypergeometric function as the same as the continuous Painlevé 6. So if we take the limit equation, so we take some case 3 is a very simple case, so we take limit t equals 0. Then A goes to the some quadratic. It's a linear equation. Then the equation y0, x0, y0 can be solved by basic hypergeometric equations, like this one. This is the solution of the this linear equation. That's why we can determine connection problem of linear equations, because connection problem of Q hypergeometric equation was solved by Watson in Cambridge, 1910. So this is the Watson's connection formula, published in 1910 in Physical Transaction in Cambridge University, and you can find this formula in the page 104 in Gaspar Rahman's room book. I talked with Professor Rahman yesterday. He wrote this formula in his book as some historical reasons, just historical reasons. He never used Watson's formula in his study. But you can find connection formula in Gaspar Rahman's book. So main theorem is we can determine connection matrix of the solution 3 for QP6 between x equals 0 to x equals infinity, like this one. And each matrix element can be represented by theta constant, like this one. I am to the detail about the very, very long sequence like this one. And I should comment one special formula. I denote LQX. This is my notation. this is same as log x over log q. It's some kind of log q x like this. It is so you like log natural x equal log e x. This is analogy of LQ. This is my notation, but I'm not sure other one wants to use my notation, but I use LQX is log QX. The basement is Q. Well, anyhow, so this is the connection matrices. This is also theta constant. Okay, so QP6 is some very good because some of the singular points at x equals 0 and x infinity is in a sense regular singularity. So there are no good definition of regular singularity in linear equations, but anyhow, QP6 has regular singular points at 0 or infinity. So that's why it's very good. How about QP1? QP1 appears in the talk in the morning, like this one. But this one is different from QP1. It is Sakai's A71 solution, like this one. F bar, so I will forget the notation. F bar is FQT, and F rho bar is FT over Q. This is a second order nonlinear Panev equation. And its limit is a continuous Panev 1 equation, and it has no parameters. Recently, Sakai student Nishioka solved this QP1 is transcendental in the sense that it has no rational solutions and it has no solutions reduced to first order nonlinear Q equations. So there are no reductions in this. So all solution is transcendental. This is solved by Nishioka, Sakai student. If you are an expert in Panev equation, you may remember the name Nishioka, who proved the transcendence of the continuous classical Panev 1 in 1984. This Nishioka is the son of Nishioka. Anyhow, so his son, so Nishioka father proved the irreducibility of the continuous Panev 1, and Nishioka Jr. proved the irreducibility of q Panev 1. It's a very, very excellent. Okay, so QP1 has only one singularity at t equals infinity. How about local solution around t equals infinity for QP1? Of course, we can. This is a very, very easy calculation. So there is a unique formal solution of this form. Oh, sorry, I mistake. This is minus ANQ minus T minus N. So this is a asymptotic solution around infinity. So I'm sorry. ANQ T minus N. Sorry, T minus. It's around the infinity. And you can determine NQ recursively like this formula. Of course, you may understand there is some alternative signature and quotient is some alternative, so like this or something. So like this. So if you set beta n equal n minus 1, 2 equals nq equals like this, and CNJ is symmetric. All CNJ are positive numbers. So as a Laurent polynomial of Q, Q has a degree beta n. So second order. That's why F is the divergent series for Q equal less than 1 or greater than 1. This is divergent series as expected. Of course, the continuous Panev 1 has only divergent series at t equal 1 infinity, like some Boudreau solutions or some asymptotic solutions appeared in the morning's its talk. Okay, how about norm of Q equal 1? This case is also some expressional in Q analysis. How about it? So in this case, Q equal E over I theta, then all AJ can written by cosine functions like this. So all real. And of course, NQ is like this. So Q equal 1 in this case is the most top down. So that's why NQ is less than N1. It's evident. It's very, very simple. And N1 is, so this is also calculated like this one, like this series. What is this series? You can, so someone notice this is hypergeometric. It's very evident because if q equal 1, QP1 reduces the algebraic equations. F4 equal t equal 1 minus f, so QP1 is like this. If q equal 1, f bar, f underline is also the same. That's why this is algebraic for quadratic equation. And you know, quadratic equation can be solved by generalized hypergeometric functions like this one. And this is also convergent. That's why it's F convergent in case all of the q equal, the norm of q equal 1. And of course, if the q is the root of unity, F is algebraic. And if q equals some root of unity of 6th root or 4th root, then all nq1, nq is integers. And they all can be represented by a generalized hypergeometric series. So remember also the Wednesday's Perlberg's talk. So he shows some limit. Okay, let's finish. So Perlberg gave some of the limit. So it's a generating function of the Catalan numbers. Generating function of the Catalan number is algebraic, but he has some limit to area functions. So this is the same as Perlberg's talk. It's some analogy. And this is also analogy of Okamoto Okumura's unpublished work. Okamoto found this one 10 years ago. So P1, P2, P7, P3 has algebraic solutions over finite number field. So if Q is a root of unity, it's an analog of the finite number field. So it's also the analog of the Okamoto Okumura. So okay, lastly, I'll list up the hypergeometric series for special q equal 1, minus 1, e or some or like this. G1 due to this series, generalized hypergeometric series like this one. Okay. So summary is, so classical Painlevé equations has a monomeric solution around Riebeck type singularity, and this is monomeric solvable. In the same way, cube Painlevé equations, so 4, 5, 3 has monomeric solution of Riebeck type singularity. It's also connection solvable. And cube Painlevé equation case and 1 to 4 case, I don't have the connection data, but symmetric expansion into infinity is divergent. But if the norm of q equal 1, it is convergent. So this is a completely new result because I found this theorem when after I arrived in Cambridge 2 weeks ago. So this is a completely new result. So this is a new result, and I hope this is may be developed more and more later. Thank you very much.
Are there any questions?
So, do you have any idea in a geometric sense where these points lie on the relevant spaces of initial conditions?
Pardon me?
Well, so for instance, in the first case you talked about where you put this commutator condition monodromy,
yes,
so there's this cubic surface.
Yes.
And you're getting these 2 points on that cubic surface that correspond to the nice solutions. Is there a geometric description of which 2 points those are?
So it is some fixed point. So in the cubic space, if you look at the cubic space,
so this is cubic surface.
Cubic surface, there are some transformation in the cubic surface. It corresponding to some braided group action of the some t change to 0 or t change to 1 or 1 change to infinity. There's this braided action gives some rational action of the cubic surface.
Okay.
And our solution, the monomeric solution, my if my mj equals 0, this is a fixed point of this braided action.
Okay.
Is that a point or does it have dimension?
0, dimension 0 point. That's 4 points.
When q equals 1, can't you also relate this to the autonomous limit as well? I mean, the autonomous
No. So we should take care of some more slightly delicate limit. So q equal. So I take the q equal 1 only the equation level, but you should consider the solution level.
Yes.
So you should take some more delicate limit.
Yeah. Okay.
So it's like a Perlberg talk. So So not yet. It's more very, very difficult problem.
Any other questions? If not, let's thank the speaker again.